Hello, I'm Sarah Todorovikj, and welcome to the talk on how good can an individual's conclusion endorsement be predicted. Let's start with an example of a conditional reasoning task. You are given, if a balloon is pricked with a needle, then it will pop, and you're given the information that a balloon is pricked with a needle. Then you're asked, how likely is it that it will pop? And you need to provide an answer between 0 and 100. Reasoning tasks like this are an example of experimental data to which cognitive models are fitted and analyzed in order to help understand human cognition. But now we ask ourselves the question, is it possible that such cognitive models can actually predict an individual's answer? Given the same task as before, you provide your answer between 0 and 100. Would it be possible that a cognitive model predicts the exact answer between 0 and 100 that you would give? This might seem like not a very difficult task at first, but let's consider a conditional reasoning task about the balloon again and imagine that the balloon is without air. Then it would not pop and your answer would be much lower. Such an event is called a disabler. Similarly, we have events that would enable the balloon to pop even if it hasn't been pricked by a needle, and they are called alternatives. Based on which events an individual has in their mind, they could give very different answers between 0 and 100, and here is where the challenge to predict an individual's answer rises. Before we dive into this, let's have a quick refresher on the conditional reasoning domain. Conditionals are statements of the form if X, then Y, where X is called the antecedent and Y the consequent. Given a conditional rule, also called a major premise, in a current state of one proposition, also called a minor premise, a conclusion can be inferred. In this table, the four inference forms are shown. For example, given a rule, if x then y, and given that x is true, we can conclude that y is true by following the modus ponens inference form. Now let's briefly talk about cognitive models for conditional reasoning. We are interested in the so-called Bayesian paradigm of models, which focuses on conclusions being endorsed, typically with a probability value between 0 and 100. Such endorsements are then expressed through conditional probability. We focus on two models from this paradigm, the Oakes-French-Chater model, or also OC from now on, which uses three parameters that expresses the probability of the antecedent, consequent, and the exception, and the dual source model, which is an extension of the OC one and assumes integration of knowledge-based and form-based components. The details of these models will be explained later. Now that we have all the necessary background information, we present our goal, which is evaluating the predictive power of models. A model is considered to be predictive if it is able to predict unseen answers of a reasoner after it's provided with observations of other participants' endorsements. Normally, a yes-no answer would be easier to predict as it is a 50-50 chance, but here we're dealing with a bigger challenge, which is predicting a single value in the interval between 0 and 100. We pose two research questions. First, how can we develop a predictive task setting and evaluate the predictions? How can we adapt and evaluate existing cognitive models to provide this prediction? Additionally, given these current models are probabilistic, is it possible to have a competitor model based on mental models? Let's first dive into the experimental data and cognitive models that we used. We used the experiments 1, 3A, and 3B presented in Zingman et al. In 2016. 199 participants provided endorsements between 0 and 100 for four contents that have varying amounts of disablers and alternatives being quantified with few and many. Additionally, each content has been presented as a full inference and a reduced inference by omitting the conditional rule as shown here. Now, the Oxford-Cheater probabilistic model. As already mentioned, they use three parameters, A being the probability of the antecedent, B the probability of the consequent, and epsilon the probability of the exception. Using these three parameters in a 2x2 contingency table, they express a conditional rule if x then y. From this table, they have derived conclusion endorsement expressions for each inference form based on the corresponding conditional probability. For example, for modus ponens, where x is given as a minor premise and we ask about the likelihood of y, the conclusion endorsement is expressed through the probability of y given x. The dual source model uses three types of parameters: xi, the knowledge-based component, tau, the form-based component, and lambda, which is a weight given to tau. Given a reduced inference, the dual source model expresses the conclusion endorsements solely through the xi parameters, which are obtained with OC's equations, making the dual source model an extension of that one. The full inference conclusion endorsement is then obtained by this weighted equation where the form-based and knowledge-based components are integrated. Now, we're going to look into mental model-based approaches, but first, we will touch upon epsilon semantics. Epsilon semantics is described by Pearl as a formal framework for belief revision. He provides a definition which is of utmost importance to us. Given a language of propositional formulas L, we define a function T that describes a truth valuation for the language L. So basically, it maps every sentence in L to the set 1, 0, where 1 is true and 0 is false. Each such truth valuation is then regarded as a world W. Finally, a probability assignment P of W is applied to the sentences in L. That means each world is assigned a probability such that the sum of all worlds' probabilities is 1. So we said we're interested in a model based on mental models. What are mental models? They are simply the truth states of a premise's propositions. So for example, given a conditional if x then y, the initial mental model that would be created is xy, meaning that both x and y are true. Using this representation, we have the mental model theory, or MMT for short, which assumes that once the initial model is created, the recollection of relevant facts and knowledge is triggered. That leads to either the initial model to be confirmed as correct, or one engages in a search for counterexamples, leading to an extended, fleshed out representation as shown here. It should be noted that this representation does not include the option for x to be true and y to not be true. And now we combine the information on mental models with Pearl's definition of epsilon semantics. We take all of the truth states of the propositions x and y, including the one that the MMT did not take into consideration. We assign 1 and 0 for true and false to x and y, and we obtain these four possible worlds to describe a conditional. Finally, we assign a probability value like P1, P2, P3, and P4 to each one of them. Based on the definition of conditional probability, we can straightforwardly derive these equations to express conclusion endorsements. We call this model epsilon MMT. Now, we have two established cognitive models, and we proposed an idea for a mental model-based probabilistic model, epsilon MMT. We remind ourselves of the main goal here, evaluating the predictive power of models. For that, we used C-Cobra, which is a modeling framework in which these three models were implemented. In order to handle endorsements in the range between 0 and 100, the absolute difference between the true answers and the predictions is taken into consideration. The lower the absolute difference, the closer the prediction to the true answer, meaning a better model performance. We also set a lower and upper performance bound for the three models by including a random model as a lower bound. It gives a random value between 0 and 100 as a prediction. As an upper bound, we have a most frequent answer, or MFA model, which takes the median of the responses for each task and gives that as a prediction. Here we have the results. We can see that the random model on the far right is our lower bound and has the highest absolute difference of 38, meaning it has the worst performance. Then we have the three cognitive models, epsilon MMT, the DSM, and OC. Each one of them have an approximate mean deviation of 17, being much better than our lower bound. However, none of them perform better than the upper bound, which is the MFA model, having an absolute difference of 16.87. All these three models use different representation. However, the results are incredibly comparable, which suggests that there is some functional equivalence between them. Since the lack of difference in performance doesn't allow for strong conclusions to be made, we also looked into the model's parameter values and how their different representations can help with learning how individuals interpret conditionals. Additionally, we looked into whether there was one model out of the three that made the best prediction for a significant majority of the individuals. But we found out that that was not the case. Around 40% of the individuals were best predicted by OC, another 40% by DSM, and the rest by epsilon MMT. So we decided to integrate the model strategies into one so-called ensemble model, which simply takes the model that made the best prediction for each individual. With that, we surpass the upper bound, and more importantly, we emphasize how there is not one single model that can capture every single individual. To conclude, in this work, we asked and answered the following questions. Is it possible to predict endorsement in the range 0 to 100? Yes. We designed a predictive task with which we showed how three cognitive models can rather successfully predict individuals' answers. Given the current probabilistic approaches, could we also have a model-based approach? Yes, we proposed epsilon MMT. It is a mental model-based approach which can compete with already established Bayesian models like DSM and OC. Additionally, what does the performance tell us? Well, these comparable results suggest a functional equivalence, but also it is interesting to point out how in this predictive scenario, a more complex model like the DSM is not significantly outperforming a very simple model like the classical OC. And from here, where do we go? What are the next steps? So we introduced a new model testing paradigm that focuses on predictions, which showed us how models have a functional equivalence. The first naturally following question would be how could parts of these models be translated into each other? Where do they actually deviate? Can we learn something about missing reasoning strategies when modeling an individual? By aiming for a better individual predictions, we can tackle these questions in the future. Here are our relevant references, and thank you very much for your attention.